joint work with Hongjin Liang. So we all know about locks. We use locks in concurrent programs to do mutual exclusion. Now the question is, what are good implementation of locks? Or in general, what are good implementation of objects with partial methods? By partial method, I mean the method like acquire, which may not always return. Actually, under some conditions, it's supposed to not return. For instance, if the lock is not available in this case. So if we care about the correctness, if it's just about safety or functionality, then linearizability still serves as a good definition in this case. But if we consider progress properties, these are the properties proposed in the literature, the wait freedom, lock freedom, starvation freedom, and deadlock freedom. But none of them applies to locks. Actually, also for lock implementations, actually, they are, even if they are useful, they're good, they are not equally good. So here we have different examples. We have the so-called test and set locks. So here we use this atomic compare and swap instruction to implement the lock. So if the lock bit L is 0, which means it's available, atomically we set it to 1 to acquire the lock. Otherwise, we do another round of loop to retry. So this is a simple implementation of a spin lock. And we know it's not fair, so it may cause starvation. Okay. And then an alternative is this ticket lock. So here we don't have to worry about the details. The idea is to simulate the queue management system in banks. So when you come, you get a ticket number. So when the number gets called, you get served. Here, essentially, all the clients trying to get the lock from a queue. So this is a fair implementation of a lock. So we have different implementations. Now the question is, how do we formally distinguish them? How do we tell the difference? Okay, this is the first question. The second question is, what are the good abstractions for them, if we care about progress? So here, by abstractions, I mean that given a concrete implementation, we want something simpler at a more abstract level, so that from client point of view, this implementation is as good as this abstraction. So this comes to the idea of a contextual refinement, which says O is a contextual refinement of A if for all clients, the behavior of C with O is a subset of the behaviors of C with A. So in this sense, A serves as a context-independent abstraction for O. And so this is some very nice property. Also in the literature, there have been relationship established between the classic correctness definition and contextual refinement. For instance, for linearizability, we know that it's equivalent to contextual refinement if we use atomic operation as specifications. And there have been similar results for linearizable objects with these progress properties. Here, this P ranges from this wait freedom, lock freedom, starvation freedom, and deadlock freedom. And correspondingly, this side, we have the so-called progress-aware abstractions. So we really want similar results for locks or objects with partial methods. We want similar property here. But as I just explained, so first we don't even have good definition of progress properties. And correspondingly, we don't have good abstractions for contextual refinement. So why this is bad? Theoretically, this means that we probably don't understand lock very well. But more importantly, practically it means that this actually affects our ability to do compositional reasoning. If we look at this simple lock-based implementation of a counter, so we just, in this lock-protected critical region, we increment the counter by 1. If we want to tell if it's, want to talk about its progress, and say if it's starvation-free or deadlock-free, we cannot answer the question without looking into the implementation of locks. Actually, it's even worse than that. If we use the locks in different settings, we have to redo the verification of acquire and release for each context. This is some lesson we learned in our previous work, which is really painful. It's just not compositional. So then we try to address this problem in our work. The first contribution is that we propose 2 new progress properties, which we call partial starvation freedom and partial deadlock freedom. Actually, the traditional starvation freedom and deadlock freedom can be viewed as instantiation of our properties. And then we provide abstractions to establish this contextual refinement here. And then we establish this equivalent result by giving an abstraction theorem. to show that the equivalence holds. And finally, we provide a program logic which allows us to verify linearizability together with PSF or PDF. Okay. So let's first look at this progress properties. We want something to distinguish the two different implementation of locks. And if we look at the test log and look at this client, so on the right-hand side, so the thread just in this infinite loop, it acquires the lock and releases it immediately. Then we know that it's possible for the left-hand thread to never acquire the lock, so that it may never print out 1, even with fair scheduling. But this is still not too bad. So this is still acceptable implementation of spin lock in some sense. That's because if we look at the whole program, it's still making progress. So the failure of this occur is because the other thread is always successful. So which means it guarantees that there always exists a method call that returns. And if we just look at this part, it's just the standard definition of deadlock-freedom. Okay. But except that for locks, we need some one more side condition here. So we say unless the lock is never released by the client, this is needed to rule out non-termination caused by a bad client. So here, this is a bad client that causes deadlock. So this thread on the right acquires the lock, and then it never releases it. So for this occur, they may never terminate. So in this case, there's no acquire method that's terminating. But we should, in this case, we should blame the client instead of blaming the lock implementation, right? This is essentially what we expect lock to do. So that's why we have this side condition. So then we get a relaxed version, which we call partial deadlock-freedom. This is not a real definition, it's just to give you some idea. Because this is just an instantiation for locks. If we want to make it work for general objects with partial methods, we have to generalize this condition. And then for this ticket lock, it's fair, so we know that it must print out 1 in this case. But of course, we need a fair scheduling. And so the guarantee here is that every thread must return under fair scheduling. And this is essentially the standard starvation-freedom definition. And again, we need this side condition to rule out non-termination caused by a bad client. So this is a weaker version, which we call partial starvation-freedom. Okay. So now we have a PSF and PDF. So test log satisfies PDF, and ticket log satisfies PSF. So we can distinguish them. So how about the abstractions? We want some abstraction to give us contextual refinement. Okay. And the first idea that comes to our mind is to use this classic await command. So most of us know about this. The idea is that if B is true, then we execute C atomically. And also, the testing of B and the execution of C is also atomic. And if B is false, it has to be blocked. So we say it is enabled if B is true, otherwise it's disabled. Also, this classic atomic blocks that have been used in previous work for concurrency verification can be just viewed as a syntactic sugar for await true do C, right? And then with this command, we can just give very simple specification for lock. So for acquire, it says we have to wait until lock is available, then we acquire takes this lock. So this is very simple. And so more generally, we want to use this await lock to fill this hole here. So we want to use it to achieve contextual refinement. And there are good reasons that we like this abstraction because first, it's atomic, so which allows us to capture linearizability. And second, it's partial, which means that it already, in some sense, captures progress. And the goal of our work is to describe properties of partial objects with partial methods anyway. But unfortunately, this is not sufficient. The weight itself is not enough. One of the major problems is that actually it's now very sensitive to the fairness of scheduling, like the so-called strong fairness or weak fairness. To see the problem, so let's look at this client again. And now this time we view this abstract await command as an implementation of lock. So in this case, we know still for the left-hand side, it may not print out 1. This is because even under fair scheduling, it's possible that whenever the left-hand thread is scheduled, the lock has been acquired by the right-hand side, which means the await block, the await command is disabled. So although it's scheduled an infinite number of times, but it's always scheduled as the wrong moment. So this is called the weak fairness, and it doesn't guarantee progress. right? And if we want to guarantee progress, then we need a stronger notion of fairness, which is called strong fairness. Essentially, it says that if, in this case, if the await command is enabled infinite many times, then the thread must be scheduled at least once when the command is enabled. Okay, so it guarantees progress. And if we compare this with our two different implementation of logs, we'll see that for test log, and then it may not print out 1. And also the behavior here is the same, no matter it's strong or weak fairness. The reason is that in the log implementation, there's no await command. Each individual command is total, is non-blocking, so that then strong and weak fairness are equivalent in this setting. And similarly for ticket logs, it must print out 1 under fair scheduling, but in this case, still, it doesn't matter if it's strong or weak fairness. So now we have this table. We have this client, and we have 3 different log implementations. We have 2 different fairness, and this is a summary of the behavior of the client in these different settings. So now the problem becomes obvious. As I explained, the first problem is that this atomic partial spec, this await block, is sensitive to fairness, which means that if we consider just ticket log, for instance, its behavior is the same for different fairness, but await has different behaviors, which means we cannot just use it for the implementation under different fairness. Okay, and even if we just look at the same fairness, remember we have 2 different progress properties here. We have a PSF and PDF. They have different behaviors, which means we can't use the same await block for these 2 different progress. So if we summarize the problem here, we have 2 different progress properties. We have different fairness, and which means that we may need as many as 4 different abstractions. This sounds pretty scary because we probably don't want to design each individual abstraction for each setting. Now the question is, can we systematically generate all of them? After all, this is about the log. It's about the same functionality, just about different progress properties. So the solution here is to design some kind of code wrappers, which is just syntactic transformations that turns each await block to some proper specifications. Now the specification is general, it may not be atomic. So the idea is to introduce the notion of general specifications. In addition to this atomic await command, it also includes some composition of this non-atomic composition of atomic operations. And then our wrapper is just a syntactic transformation which turns await to these general specifications. Also, it's parameterized over progress properties and fairness. Okay. And so this is the goal is to fill this hole here to have a contextual refinement. How do we use our wrappers? The idea is the following. We still ask the programmer to provide this abstraction in the form of a await command, because as I explained, it's so simple and intuitive. Also, it captures linearizability, but it just doesn't work in this place. And then we apply our wrapper so that we hope that this derived specification may give us a proper abstraction. And then, of course, the next step is to define the wrappers. And we have these 4 combinations. We need a wrapper for each combination. So here I don't have time to give the details. And just to give you some idea. So here, the way we define wrappers is to introduce auxiliary variables and some auxiliary code. Sometimes we need to add some more progress, and sometimes we may reduce progress. So here, like for this corner, then we could just do this identity transformation, which itself is a good abstraction. And for this corner, we probably need to add more progress by introducing a waiting queue. And this is probably a tricky one. So actually here, a wait block actually provides more progress than needed. Then we need to add some delay mechanism, add more interference. So as a summary, we have wrappers for each individual combination, and this gives us this abstraction. Now, is this a good abstraction or not? So we still want to have this result to show that it's equivalent to the linearizability and the progress property we proposed. And this is our abstraction theorem. It establishes this equivalence. And so actually, this is a very important theorem because on the first hand, it justifies our definition of wrappers, which means the abstraction is not too weak. It guarantees the PSF and PDF. So on the other hand, it justifies our PSF and PDF definition because it gives us this contextual refinement, right? So the last piece of our work is a new program logic, which allows us to verify the object implementation with respect to this await command. This is the atomic partial specification. This is just a simple extension of our previous work on LiLi, which is logic for starvation-freedom and deadlock-freedom. And we proved that this logic actually guarantees this contextual refinement. And then remember, we have this theorem showing the equivalence. So this means that this program logic allows us to verify linearizability together with progress properties. Okay. So as a summary, we we studied the progress of objects with partial methods. So we have 2 new progress properties proposed here. And also we have 4 wrappers to enumerate all combination of the progress properties and the strong and weak fairness combination. And then our abstraction theorem shows the equivalence here, and we have a program logic to verify progress. Thank you.
There are no online questions, so.
Can you move to the previous slide? So what is this X instantiated into? Because on the left-hand side of this equivalence, there's no instance of X. And then on the right side, X could be instantiated either to strong or weak. P, of course, I assume the P on both sides is same, right?
Right. So this is cheating because P is parameterized. The definition of P is parameterized over chi, over scheduling.
Oh, chi.
Yeah,
okay,
yeah.
So the black P is really a combination of a P and chi.
Yes.
Okay. The second question is, so in practice, just merely have starvation freedom is probably not enough because I know I want to starve, but usually we prefer bound, so I want to be starved because, something could still may not starve, but you have to wait forever, 1 million years. Right. Is it possible to impose a bound on these properties so that, instead of knowing starve, knowing that you would actually get served within certain bounds?
Okay, so we have never thought about that. I think if we just extend our definition of PSF or PDF, it's probably not difficult to introduce bound. But if we also want this abstraction theorem, then I think the underlying semantics have to have the notion of execution step counting, something like that. But
right.
we don't know.
Yeah. Okay.
Thanks.
Hi. I just want to ask about the wrappers. Are they generic over any kind of partial method, or do they, as you present them, work only for the locks?
It's generic for any objects with a partial method.
Okay.
So we have, in our paper, we have examples like partial stack. For instance, when you pop the stack, if it's empty, you have to wait until somebody push an element. So it's for general ones. Yeah, it's not dependent on the functionality of the underlying method. Yeah.
So if I have some other implementation of locks, how would your techniques help me figure out what liveness and liveness properties they have?
So basically you're asking the PSF and PDF may not complete to cover all cases. Is that the question?
That's one of the possibilities, yeah.
Okay, well, I don't know. We certainly don't claim completeness, but we think this is probably something, you know, it's enough to cover the examples we have. Yeah.
And the second question, you have 4 theorems which appear to be pretty much independent. Was there much commonality involved in proving them?
Well, so you mean for different instantiation, the proof for each case?
For the 4 theorems,
Right,
yes.
right. I think the structure is pretty much the same, but each case has its own tricky part. So yeah, but the infrastructure, the proof structure is the same.
Thank you.
Any more questions? Okay, thank you.
Thanks.